Okay, so let's continue from the last lecture and we will finish the thin airfoil theory, right. So, okay, so where we had stopped was that getting an expression for the zero normal boundary condition on the streamline, right. Okay, so so essentially if I were to do this again, okay, that and this is the camber line that we are looking at, right. So, and of course, okay. So, this is the camber line that we are looking at when I say here, okay. So, okay. So, for a thin airfoil, so basically I am distributing my vortices on the x axis, right, but I am still satisfying the zero normal boundary condition on the streamline. Okay. So, say at this particular point P, so this is my stuff. Okay. So, so essentially for a thin airfoil right. So, we need to find an expression for this, okay, such that we still we satisfy the boundary condition on the camber line, and here the camber line is still the streamline. Okay. So, the chord line is not the streamline, the streamline is still the camber line, okay, which means I still have a flow which goes that way. So, therefore, I need to calculate the zero normal boundary condition on the streamline. Okay. So, having done that, right. So, we said that so at this point we said the zero normal boundary condition, okay, the zero normal boundary condition. So, right. So, totally induced velocity due to the vorticity distribution here. Okay. So, okay, and this basically we found out, okay, we calculated this as if you see over here, right. So, okay, and okay, this is basically the slope. Okay, this is basically the slope, and this is the angle of attack alpha, right. So, therefore, this V infinity n, okay, it came out to be sine of theta plus this, right. And we had also found out that, of course, if you see from here, if you look from here, right. So, if you look at this, right. So, therefore, if when I am going to write this, okay, so what I get here is that now V infinity, okay, now V this, okay, if I were to write this, okay, and therefore, I can also write this as theta okay. So, this is what we get out here. Okay. Now, if we consider this to be a small perturbation problem, then you know that if theta is small, then I can write tan theta theta, right. So, from here if you see, so theta is tan inverse this. So, therefore, here theta I can just simply write this as this theta I can simply write this as dz by dx. So, basically, therefore, I will write my normal component okay, this, right, where right. So, this is v infinity sine of alpha minus dc by dx, and the alpha is in radians. Okay. Okay. So, therefore, we get this. Okay. Now, let us get the normal component of the induced velocity, right. So, if I say look at it this way. Okay. So, again, okay, and I have essentially a vorticity distribution like this, right. So, now if I have something like this, okay. So, let me take this, let me consider, okay, this distance to be z, okay. Let us say we will consider this to be z, okay, and this element here to be dc. You understand? So, basically z goes from, say, goes along x. So, you can say that z is essentially goes from 0 to c on the chord length, right. So, at a particular c, take a small element of dc, okay, over here. So, therefore, now how will we calculate? I mean, what is the we need to get an expression for this this component out here, okay, induced velocity due to this distribution. So, if you remember, this is so velocity distributed, okay. Okay, this is a standard expression. So, any standard book should give you this if you do not remember. Okay. So, so therefore, in this particular case, the way we would write this here, okay. So, the total, say, velocity distribution, okay, in this case would be, okay, the gamma is distributed over this, say, z into dc, just going by this expression here, okay. So, dc, which is ds over here, 2 pi, and r is any distance between any point and the location of this, okay, 2 pi. So, it would be x minus c. Okay. So, if I do that, okay, this is dw, and the total velocity distribution, therefore, so the entire velocity distribution over this airfoil would be, so I will write that basically here. So, your, okay, I will write this as okay, and what we basically need to do, that this goes from, this z goes from 0 to c, isn't it? So, the 0 goes from 0 to c, and let us write this as, let us store this up, okay, and call this as, say, this. Okay. So, now therefore, what we have here this, or so if I write this down now, the expressions for this. So basically this is it, okay. Okay, and this is equal to, okay. So this is nothing but the so this is essentially the statement, okay. So if I'm going to box this up, so okay, so this is essentially the statement of the thin airfoil theory, okay, which is nothing but the imposition of the zero normal boundary condition, okay, where the camber line is a streamline, okay. And in this particular case, we are considering the airfoil to be thin enough so that we distribute the vortices on the chord line instead of the camber line, okay. So basically, instead of saying ds, which is a curved line, we just take dc, just makes our computations a little easier. So that's how we take care of, basically we kind of linearizing, using a linearized theory to do this, okay. So this is our thin airfoil theory, okay. Now let us go back therefore to the problem that we were trying to solve, okay. When we set out to solve this, and go ahead and see how we will use this linearized theory to get the coefficient of lift and drag, right, for the flat plate. So if I may sort of remind you what we were going to do, okay. So essentially we said we had a flat plate, okay, the problem of chord length of a certain chord length c, which is at an angle of attack of alpha in a supersonic free stream. So use a linearized theory to calculate the CL and CD. So basically what when you use a linearized theory, what now by now you should be understanding that when you use a linearized theory and add a correction to it, then we should get an expression for CL and CD in the supersonic stream, okay. Because we're talking about compressible flow, okay, when you're saying supersonic free stream, whereas you're saying use linearized theory, which would not be compressible. So how would we sort of go about here, okay. So okay, now a little bit of geometry here, okay, little bit of geometry. So if we start with this problem now, okay. Now okay, let's call this C as we have done this, okay. So say this is the origin, okay. Now if I use spherical coordinates here, how would that look like, okay. What does that mean? So if I say use spherical coordinates here, okay, if I do this, okay. So say I have this, so I have this radial line, okay. I have this radial line here. Now this is my airfoil, okay. So basically, if what I'm saying is, if I have my airfoil over here, which in this case is a flat plate, okay, this out here is my flat plate, okay, and this is the this is a flat plate of length or chord C, right. So which is what we have here. So in this particular case, so if I take a spherical coordinate system, okay, so then this is my one radial direction, which in this particular case is equal to c by 2. Right. So, I am basically taking the center of this and drawing a curve, circle, which is half circle rather. So, of radius c by 2. Okay. So, in that case now, okay, if I say drop this perpendicular from here. Okay. So, then okay, now this distance, okay, this distance is basically z. Okay. So, this distance is z. So, you can say at this particular point out here, okay, here the x location of this point is z, if I do this. So, from here we can see, okay, from here we can see basically, okay, let us say this is, so say this is C, right. If you take this triangle ABC, okay, if you take this AC, okay, AC is r cos theta, okay, which is c by 2 cos of theta, right. So, therefore, z, okay, z is equal to this z, okay, which is essentially OC, okay, is OA, okay, minus AC, right, and or OA out here you can see this is another radial line. So, that is C by 2, okay, minus AC is C by 2 cos of theta, okay, or Z is equal to C by 2 1 minus cos theta. Okay. So, this is the relationship. So, this z coordinate, if I write in terms of the chord length and this angle. Okay. This, so therefore, from here dz would be what, right? Okay. And of course, also if you can see from the geometry here that if I write it here, so at theta equal to 0, at theta equal to 0, okay, z is equal to 0, and at theta equal to c, c is equal to, sorry, theta equal to pi, okay, z is equal to c, right. So, this is just the, this is just to, the geometry, this is talking about the geometry if I were to use this coordinate system. Okay. Now, in this particular case, what we have is a flat plate. Okay. So, the camber line out here is a straight line, okay, is a straight line which is having an angle of attack of alpha, which would mean what? Okay. Okay. So, let us come here and say look at this. Okay. Let us sort of draw this picture out here. Okay. So, what we have, if you look at this in this particular case, okay, so we have a camber line like this, okay, which is at an angle of attack alpha here. Okay. Now, instead of this, what we have here, let us just erase all of this. Okay. So, what we have right now, let me draw it here and show you sort of the comparison. So, what we have here okay. Now, if you look at this, what we have here, say okay. So, this is a flat plate. Okay. This is a flat plate which is making an angle alpha. Okay. It is the same thing. Okay. You could keep that horizontal along this and give it an axis, or you and basically. So, what we are saying is in this particular case, of course, is that we have a free stream which comes like this. This is my free stream. Okay. So, you see here, this actually is now the streamline. Okay. And compare that with this over here. So, this is my streamline, and again this is 0 to C. The chord length is 0 to C. Okay. Therefore, if you look at this over here, dz dx, okay, is equal to what? This is the slope which is minus alpha, isn't it? So, this is dz dx over here. Okay. So, therefore, the right hand side, if you look at this, this is the thin airfoil theory. So, this is the right hand side actually. This is the right hand side of this equation, the thin airfoil theory. Okay. So, which is V infinity sine of alpha minus dz dx. Okay. And using smaller, if this angle is small enough, then we can just write as V infinity into alpha minus dz dx. Okay. So, therefore, writing that, so right hand side, using the right hand side of the statement of thin airfoil theory. Okay. So, there the way we would write that is essentially okay. Okay. Isn't it? And in this particular case, okay, dz by dx is minus alpha. So, what we have over here is okay, or okay, this is the right hand side of it. Okay. So, the next thing, of course, so basically we are just applying the thin airfoil theory to this particular case. Okay. Okay, let's look at this, I guess. So, we have a z which we are, this is our geometry now. Okay, this is our geometry where our z is this and our dz is this, isn't it? If I write that in terms of spherical coordinates, okay, then we can basically let the integral go from 0 to pi. Okay. So, using I'm going to use that, okay, and write this down here first. So, z is equal to c by 2, okay, and dc is equal to c by 2. Okay. So, in this particular case, okay, in this particular case, therefore, so what we have over here is that d, okay, w. Okay. So, in this case, therefore, it becomes what? So, this gamma I will write that in terms of theta, okay, and ds is dz here. So, which is c by 2 sine theta d theta by 2 pi. So, r, the total is c by 2, okay, c by 2 minus z, okay, c by 2 minus z, which is okay. So, this is for the total derivative. So, this comes out to be okay, let us do this here. Okay. So, c by 2, this would go, right. So, what we would have over here, okay, so what we essentially would get over here is gamma theta, okay, sine theta, okay, sine, okay, and this d theta, now we are basically going for the this thing, we are going for the entire plate. So, then you do that and then you get this into 1 plus cos theta, right, is that right? Yeah, okay. So, this is the left hand side of it, okay. So, if I were to, so therefore, I can say, okay, in this particular case, this is my left hand side, okay, this is the left hand side from the thin airfoil theory, okay. So, this is the total induced velocity from the vorticity distribution, okay, and we have got an expression for the entire normal component of the velocity, okay, for this flat plate, okay. So, now let us use this, having basically just applied the thin airfoil theory here, let us use this now, okay. Okay, so we have done this. Now let us go ahead and calculate what we set out to do initially. Okay, so what we will do now. Okay, so therefore, so let us now get an expression. Therefore, equate these two and get an expression for this gamma theta over here. Okay, so now what we have over here is that gamma theta. Okay, into okay. So, this is the okay. So, this is the left hand side and the right hand side. Okay, this is essentially the thin airfoil theory applied to this particular problem. So, linearized theory applied to this particular problem. So, when I do that, so what I get basically, if you look here, so an expression for gamma theta, which is equal to 4 alpha to 1 plus cos theta by sin theta into v infinity. Okay. So, this is the expression for gamma theta. Okay, this is the expression for gamma theta. So, this is the distribution. So, therefore, total circulation. Okay, when we calculate the total circulation, okay, then we will be able to calculate the total lift and total drag. Okay, so total circulation therefore is essentially gamma, okay, which is okay. So, total circulation, if you do this, so in this particular case, of course, we will write this to we will use the theta coordinates, okay, and we will go from 0 to pi. So, we will use gamma theta and dz as we have used before. Okay. So, that is c by 2 sin theta d theta, right. This is the total circulation. We will bring in this expression of gamma theta into here, okay. And when I finish the, okay, let me do this, okay. So, if I do this, let us do this here, okay. So, this becomes c by 2 0 to pi, okay. Let us see, gamma theta is 4 alpha 1 plus cos theta. This sin theta and this sin theta cancels out, okay. Then we have v infinity and d theta, okay. So, let us take 4 alpha and v infinity out. So, what we get here is 2 alpha v infinity c, okay, 2 alpha v infinity c, okay, into 0 to pi 1 plus cos theta d theta. Okay. So, this is what we get. So, if I were to sort of complete it over here itself, okay, if I use the space, okay, spare me. So, again, so therefore, my total circulation here, it becomes what? 2 alpha v infinity c, okay. What I get here is sine theta, okay, sine theta, okay, sorry, here, so I forgot the theta, okay, we are integrating here, so theta plus sine theta 0 to pi, right. So, which becomes 2 alpha v infinity c, okay. So, we get pi, okay, and pi plus sine pi is 0, minus 0 minus sine 0 is 0. So, we essentially get this. So, or total circulation is 2 pi v infinity c alpha, okay, which makes sense actually here. So, you remember what we had got earlier, so it was just 2 pi alpha, okay, for a straight plate. So, here, so the total circulation is 2 pi v infinity c into alpha, right. Okay. Now, we will calculate the CL and CM. Okay. To do that, let us say we will come over here. Okay. Let us say okay. So, what we will do now is that now lift per unit span therefore is given as right. This is the lift per unit span. Okay. So, once if I the moment I get that, so I can write this as rho infinity v infinity, okay, into this expression which we have just derived, which is 2 pi v infinity c alpha. Okay. If I do that, so then what I get here is 2 pi rho infinity v infinity square, okay, c alpha, 2 pi rho infinity v infinity square alpha c. Okay. So, this is my lift, okay, and therefore, CL, okay, CL becomes half rho infinity square v infinity square into, well, in this particular case it is a 2D airfoil. So, it is just C, right, unit span. So, if I do that, let us get this from here. So, what we get is 2 pi rho infinity v infinity square c alpha, okay, half rho infinity v infinity square into c. Okay. So, what you can see from here, what we get is that 4 pi rho infinity square v infinity square, this thing cancels out. So, essentially, if you look at this, these both cancel out. So, what we get is 4 pi alpha. Okay. So, the CL out here using the linearized theory is 4 pi alpha. Okay. And okay. So, this is our CL, right. So, then now we will calculate the CD and CL, okay, for the Mach number here, which was supersonic Mach number. It was just m infinity, right. We need to calculate that. Now, for this particular case, now what we will do here, okay, in this particular case, okay. So, let us go ahead and use our small perturbation theory and or linearization theory to connect the two. Okay. So, we have found out an expression for if using the linearized theory, thin airfoil theory, right. Okay. So, now here the normal component is 2 alpha V infinity. We have seen this, right. So, the normal component out here is 2 alpha V infinity. Okay. So, if I use a perturbation theory here, this normal component is nothing but V dash, which is this. Okay. And in if you remember right, when you used correction in this particular case, since this is our supersonic flow, we will use this parameter over here, then our U component becomes this. Okay. So, this therefore, what we get is okay. So, if you do that, now it is easy. Okay. Now it is easy. So, we get coefficient of pressure, which is okay. This is something we have done using a small perturbation, using perturbation theory. We know we have done this so many times, right. So, if I do this, so therefore, from here therefore, this becomes okay. This is 4 alpha by this. Okay. So, now if you look at this, this is the coefficient of pressure. Okay. This is the coefficient of pressure in this particular case. Okay. So, now CL, okay, CL is the lift. Okay. So, which is Cp cos theta. Okay. So, if you look at this particular case over here, so then this becomes what? Okay. This becomes as theta tends to pi. Okay. We go over. So, basically what we are doing here is we will integrate this, right, the entire length of the airfoil, okay, which we are basically going from 0 to pi. So, therefore, theta tends to pi, it is 1, right. So, therefore, this becomes essentially Cp. So, therefore, our Cl, okay, for the supersonic case out here is 4 alpha okay. So, 4 alpha using this, and again of course CD we take the other component of the Cp. Okay. So, let me write that over here. Okay. If I write that over here, that CD of course is Cp sin theta. Okay. So, again this in this particular becomes Cp. Okay. Yeah. So, sin theta tends to theta. So, this becomes this particular case alpha, right. So, therefore, in here, so therefore, CD becomes 4 alpha square pi Okay. So, now you can clearly see the difference, essentially the difference between the thin airfoil theory and if we use the perturbation theory and a correction to get Cl and Cd for the same airfoil. Okay. So, I use the thin airfoil theory and I got a Cl as 4 pi alpha over here, and instead here first when I started with this, okay, I got an expression using the, if I use a perturbation theory, okay, perturbation theory here, which is again a linearized theory, okay, and use the normal component of the perturbation velocity, okay, and that would be the normal component V alpha infinity n. Okay, we use that, and then we got an expression for u dash and v dash, which is the perturbation velocities. And using that, we were able to get basically Cp. We were able to write it in Cp using the correction for the supersonic flow. Okay. So, and of course, using Cp, we coefficient of pressure, we write the Cl and the Cd. Okay, for this particular case, you can see the difference. When I use a thin airfoil theory, okay, it is basically this, whereas this I can use for the supersonic flow. So, you can see the correction here. So, essentially you can say the correction would be pi by m infinity square minus 1, if you basically if you look at the relationship here. So, I can say write this as incompressible. Okay, if I write the incompressible here. So, if I were to do that, then in this particular case, okay, so our Cl supersonic is basically pi by we can use that lambda also, we used a lambda, right, pi by lambda into Cl0. So, this is the correction we use in this particular case. Okay. So, I think we will stop here, okay, and pick up some things next time now. Thank you.